right, welcome everybody. These are the video notes for atomic models and the electromagnetic spectrum. And don't let electromagnetic spectrum freak you out. It's just the fancy academic term for light. Okay, there's lots of different kinds of light. There's a large electromagnetic spectrum, but we'll talk about that here in a second. So before we get started, you are going to need your physical notes sheet so that you can follow along with me. You will be taking these down as we go. Okay? And anytime you need to pause the video or rewind me, feel free to do so. I won't mind. Okay, so first, before we can start talking about atomic models, we need to talk about what a model is in science. And this might be review free, that's okay. But models in science are used to describe how unseen things behave or look. Okay, they can be used to predict how things we can't see will behave when we do something to them. So we're going to write models in science are used to describe how my handwriting's bad on this, how unseen things look or behave. Okay. And again, we can't see them, so it's our best guess based on evidence. So it's how unseen things look or behave based on evidence. There we go. Okay. So in chemistry, atomic models are used to describe how atoms look or behave. Okay, so we can't see atoms, they're so tiny, but we can do experiments to delve deeper and predict how they will behave, and based on that, we can predict what they look like based on evidence. Okay, so we're going to say in chemistry, atomic models are used to describe how atoms look and behave. Excellent. Okay, and what's really important about models in science is that they change. So they change based on new evidence. So let's say we have a model of something, we think it looks like this, and we do an experiment, and we get either new data or evidence that contradicts our previous model. We need to change it, okay? And so these models can change when there is new or contradicting evidence. There we go. Any new or contradicting evidence. And contradicting just means it goes against what you think you know. Okay, and we're going to do we'll go through a couple examples of just that with the atomic model. So if you go down here, we've got several models of the atom throughout history. So the atom did not always we did not always think it looked the way we think it does now. For example, long time ago, don't remember exactly how long ago, we had Dalton's model. And what Dalton's model said was that the atom was just a sphere. Okay, so elements were spheres and they looked different. So these spheres looked slightly different from all the other atoms or spheres of elements of different kinds. But they were just solid spheres. So the main feature of Dalton's model was that they were identical. Come on. There we go. We'll say they are identical solid spheres. There we go. Sorry, my handwriting is really bad on this tablet, but that says identical solid spheres. Okay. However, as time went on, people were studying the atom more and more and more, and they realized there was something else going on inside the atom. They realized that there was the existence of some negative charge inside the atom. And Dalton's model did not account for there being charges in the atom. So what they had to do is they had to change it. They had to refine it. And so the new evidence that we're going to say for our new model, which is Thomson's model, the new evidence was that atoms have charge, or charges. They can be charged. Have charge. Okay. So atoms have charge. And that led the way to a new model of the atom that accounted for those charges. And so what Thomson's model included was it was still a sphere, but instead of a solid sphere, there was a couple of different parts. So one part were that there was small electrons floating around inside of that atom. And what they were floating around in was this positively charged goo. So we've got negatively charged particles floating around in some kind of soup of positive charge. So we're going to say the main features of Thomson's model. This is sometimes called the plum pudding model because there's like the electrons are like raisins floating around in pudding. It's gross. So the features of the Thomson's model is that there are small electrons which are negative. I'll put in parentheses negative. Floating in positive goo. I'll put in parentheses goo. Okay. So that was the model of the atom at that time. However, again, as time went on, people were studying the atom more and more, and they found evidence that didn't quite fit with that model. Okay, and in science, we always have to change a model if it does not fit the evidence. Okay, so we have to change it so it does fit the evidence. So this new evidence was found by a guy named Rutherford. What he did is he took a very thin sheet of atoms. The atoms happened to be gold. And what he did is he shot positive particles at them, just positive. They were helium nuclei from a radioactive piece of material. And he shot it at them, shot it at this very thin piece of gold foil. And he predicted that if there was a positive goo in this atom, then they would just bounce right off of the positive goo because positive and positive will repel each other. But that's not what happened. What happened is instead, a lot of the positive particles went right through that gold foil, that solid sheet of gold foil. And he was like, huh, well, that's weird. Only a few of them bounced off. So he said, the positive charge in the atom must be confined to a very small space. That's why the positive charges will miss most of the time, but only occasionally bounce off. And so this positive particles pass through solid objects. Okay, so he found that positive particles pass through a solid sheet of gold foil. And so he proposed a new model of the atom where that positive goo was not goo floating around, it was condensed and a very small part of the atom right smack up in the middle, which we call the nucleus. So the new model that he proposed had a small, dense nucleus and electrons, those negative particles, he still kept, right, in his model, but they were orbiting the nucleus, okay? And so the features here, small, dense nucleus, small, dense positive nucleus. And electrons orbiting the nucleus. Electrons orbit nucleus. Boom. Okay, and those electrons orbit in just about the same distance from the nucleus, so they're kind of like a big ring around the nucleus, as you can kind of see in the picture above, right here. Okay, so now we come to a slightly more recent model of the atom, which is Bohr's model. So Bohr's model saw a couple of things about atoms that Rutherford's model did not explain, or explain well. Okay, so the new evidence that Bohr found was that when he excited atoms with either heat or light, they produced color. They produced not just a rainbow of color. They didn't always produce bright light. They produced a very unique color. They produced a very unique and very specific colors. So they did not produce all the colors of the rainbow. They only produced very specific colors. And so what he did, he said this Rutherford's model does not predict why we see these very specific colors. And I would like you to see this for yourself. So around the room, there's going to be a couple gas discharge tubes set up. I want you to grab a pair of diffraction glasses from the front. These diffraction glasses split up light into its component colors. And I want you to take a look at some of these gas discharge tubes. And you're going to look for the very bright lines that get produced by each halogen light bulb. So the glasses look like this. They're pretty styling. So you're gonna go up to the front, you'll pause the video, grab a pair of these glasses, and just take a look. Just make your rounds and look at some of the lights that are available. And you'll see here, does this work? No, not really. You'll see that it is split into specific colors, and notice that it does not produce every color of the rainbow. They produce very specific bands of colors. So I'm gonna pause that video now and grab a pair of glasses and just take a look at. Okay, welcome back. So, as you saw, that when those elements are excited, they produce very specific colors. And so Bohr, what he did is he added to the model of the atom, and this is called Bohr's model. So what Bohr's model says, it makes a couple additions to Rutherford's. So instead of electrons just being in one specific ring or one specific energy level, he said that electrons exist only in very specific energy levels, and there are different sizes for different energies. Okay, so what we're going to say for big ideas of Bohr, big ideas of Bohr models is that electrons only exist in specific energy levels. Okay, he said that there's different energy levels and electrons exist in those specific energy levels. They cannot exist between, they can only exist in one at a time. And electrons are most stable or most relaxed when they're close to the nucleus. I'm going to say that they are most stable and relaxed when close to the nucleus. Okay, that's where they want to hang out. That's where they like to be. And the second big idea of Bohr's model that he added was that electrons are excited by heat, light, electricity, whatever. They're going to jump away from the nucleus. They're in a high energy state, and they're going to jump away from the nucleus to a higher energy level. Okay? So we're going to say they will jump away from, we're out of room. Jump away from the nucleus to a higher energy level. Perfect. And then the third big idea of Bohr's model is that he said when electrons are now relaxing back down to the nucleus, what happens is that extra energy has to go somewhere, and it's released in the form of light. So we're going to say when electrons relax and fall back down to a lower energy level closer to the nucleus, they release, ooh, come on. Release this extra energy as light. And the bigger they fall, so if they're at a really high energy level and they have to fall a long way, the more energy is released. The larger the energy of light, or the greater. Larger the energy of light. Awesome. Okay, so if you take a look at this diagram up here, it shows that there are very specific rings, and the electrons can jump between those rings. And when they go from a high energy level to a low energy level, they release this squiggly thing that we call, or we see as light. Okay. So before we get too more in depth about the Bohr model, we need to talk about what is light. This might be a little bit of review for some of you. However, I want to make sure we're all on the same page. So what is light? I'm going to scroll down to the next page. So light, as we said before, is produced when an excited electron falls back down closer to the nucleus and releases that extra energy. It just happens to come out as light. Light has properties of both a particle, which we call a photon, and a wave. So you can almost imagine a particle, and it's moving along in space along a wave-like pattern. And so we're going to draw that real quick. We're going to draw a wave on our paper here, okay? And so you can imagine this particle moving along this wave in 3D space, but it's just going really, really fast. Okay, so light has a couple of different properties, okay? It has what's known as wavelength. I'm going to change my color for this one. Wavelength. Draw. I'll use green for wavelength. Okay. Wavelength is represented by the Greek symbol lambda. It looks like kind of an upside down Y. It also has a frequency. Actually, I'll just do wavelength first. We'll focus on one at a time. So wavelength, represented by lambda, is the distance from one peak to another peak in that wave of that light, a wave of light. So, for example, if I was to look at this peak and I was to look at this peak, the distance between these two peaks, that's a pretty straight line, is called the wavelength, or the distance is the wavelength. So I'll label that wavelength. Okay, wavelength, and that's the lambda symbol. So if you see that upside down Y, it means wavelength. Okay, and we will say that wavelength, we'll define it here, is the distance between two peaks in a light wave. A light wave. Okay. The weird thing about this, I'll tell you about it later. Let's go on to frequency next, before we get too far into that. So the next one is frequency. I'll change my color for this one. I'll use red. So I'm going to use thicker red. Let's see how that works. So frequency is the number of times a peak passes a certain point in 1 second. Okay, so if you imagine these peaks here, and they're moving towards you, let's say there are waves on an ocean, and they're crashing into the shore. However many waves hit the shore in 1 second is known as your frequency. But in this case, it's much, much faster because these waves are moving a lot faster. Frequency is represented by the Greek letter nu, which looks like a V with a little tail on the end, like that, the one I just drew. And it is defined as the number of peaks that pass a point in 1 second. Okay, and per second, I will just tell you because you'll encounter this eventually. Per second, there's a word for per second, and it's called a hertz. So a hertz, or it's also known as Hz, abbreviated Hz, equals 1 second. Or excuse me, I'm going to delete that. It's actually per second. So if something is 3 hertz, it means it's 3 of something per second. Okay, per second. And I'll abbreviate second, SEC. Okay. The next property that a light wave has is how fast it goes. And light is pretty simple. It always goes at the speed of light. There's rare exceptions, but we're going to assume for our purposes that light moves at the speed of light. And the speed of light is a set speed. The speed of light is 2.998 times 10 to the 8th meters per second. So that's meters per second. So it's very fast. Light moves very, very fast, which makes sense. So it's 10 to the 8th. And the abbreviation for the speed of light is c. Just a lowercase c. Okay. So these are the main properties of light: wavelength, frequency, and how fast it goes, the speed of light. And all of these 3 are related with an equation that you will need to be able to use because it's on your AP equation sheet. If you take a look at your AP equation sheet, I have mine right here. I don't know if you can see that. You probably can't. It might be backwards. Now I want to look under atomic structure. The second equation, I squared it, is the wavelength, frequency, speed of light formula that relates all these 3 things together. So we're just going to write it up here at the top corner. We're going to say that C equals, kind of looks like an E, but I promise it's a C. C equals frequency, which is the Greek letter nu, times wavelength. Okay, so if you are always given speed of light, if you don't have it memorized, it is on your equation sheet as well. It's given to you. I pointed an arrow to it. I can't see it, but this is the speed of light. So that's given to you on your AP exam. So if you know either wavelength or frequency, you know 2 out of those 3 variables, you can solve for the third. And we will do some practice here in just a few minutes. Those are the 3 properties of light. The last thing I want to talk about before we move on to light, before we move past light, is the energy of a photon. So we can actually measure the energy of just one single photon using a very specific equation. So I'm going to turn back to black. All right. So energy of a photon is sometimes symbolized with the capital E, and the energy of a photon can be described with the equation E equals H times V, or frequency. Energy equals H times frequency. And what H equals, okay, H is a new constant that we have not encountered before, but that's known as Planck's constant. It just describes the energy of one single photon, and that is also given on your equation sheet. It's the one that I circled. It says Planck's constant. So then pull out your equation sheet so you can find it really quick, just so you know where it is. So take a second to pause the video and just find your equation sheet and find Planck's constant. So yeah. So when you find Planck's constant, it is 6.626 times 10 to the negative 34 joules per second. It's a very, very small unit of energy, or it's a very small constant. That's because a photon does not take a lot, or does not carry a lot of energy. Okay. So if it ever asks for the energy of a photon, you'll be using that equation. Energy equals Planck's constant times the frequency of that specific wave of light. Okay. The reason we care to talk about light and its very specific waves and its frequencies is because depending, if we go scroll up, depending on the wavelength tells you what color or what type of light it is. So if you take a look at this graph here, we have a spectrum, or a, we go from small wavelengths to large wavelengths. And what is over here are your really, really small wavelengths, and over here your really, really long wavelengths. Notice the distance between those peaks. They get larger and larger and larger and larger. The distance between those peaks tell you the wavelength, and it will also tell you the color or type of light. So the ones that are really, really, really close together, the waves are really, really close together, those are known as gamma rays. They're very, very high energy type of light. And then as we go, as we get wider, we go to X-rays and then ultraviolet rays, which are still, all of those are pretty dangerous types of light. Ultraviolet's a little less dangerous, but it'll still damage your skin. That's what a sunburn is. And then we get into slightly longer wavelengths of light. And this is the visible spectrum. So our eyes pick up these kinds of, this wavelength of light. We can receive this wavelength of light. And that's from 400 nanometers to 700 nanometers. So a nanometer is, there's 1 times 10 to the 9th. So that's there's a billion nanometers in a meter. So it's very small still, but the smaller wavelengths in the visible spectrum are closer to purple, and the larger wavelengths are closer to red in the visible spectrum. As we get wider and wider, we get to the infrared spectrum, which we can no longer see, but some animals can see a little bit into the infrared spectrum. And then we get into radio waves, which are super, super long. Okay, those ones are like the size of mountain ranges between the wavelengths. They're still going very fast, but the particles, or excuse me, the photons are their wavelengths are very, very large. They're very far apart. Okay. The one thing I want to point out about that is that, and it's counterintuitive, as the wavelength of a wave of light, as the wavelength decreases, so as it gets smaller and smaller and smaller and smaller, a lot of people are like, oh, well, if it's getting smaller, that means the energy of the light has to be getting smaller as well. But if you take a look back up here, right, at the gamma rays, those are the really high energy types of light. And so as wavelength decreases, or the waves get closer and closer together, the energy of light will actually increase, right? So we're going to say as the wavelength of light decreases, or they get closer together, decreases, Okay. As that decreases, the waves are going to come faster and faster and faster. So if the waves are this far apart, you can think of like waves on the water. If the waves are very, very close together, they're going to hit you with lots of frequency, or it's going to be very frequent. The frequency of light increases. And the energy of that light is going to increase as well. It's because there's those photons are hitting you more frequently. It's more damaging. It hits you with more energy. Okay? So we're going to say, and the energy of also increases. Okay. Okay. Let's see here. We're good. So uses for types of light. So one of the things that it wants you to know on the AP exam specifically are some uses for various types of light. And we're going to go over visible, infrared, and ultraviolet and why they're useful. So visible light specifically, because we can see it, and we know, if we think back to when we were talking about molarity, we know that the more concentrated something is, the more solute particles are in there, the darker it looks. So we can use visible light as a tool to measure the concentration of solutions. So we're going to say visible light is used to determine concentration of solutions Bam. Okay, we're just going to say that because we can see it, we can perceive it. It's used to determine how concentrated something is. And we're going to talk a lot about that tomorrow and the next day. We'll have a lab on this actually. Infrared light, however, is used slightly differently. So infrared, remember, that's slightly longer than what our eyes can perceive. The wavelength is slightly longer. Infrared, those wavelengths, so if you zoom way, way in and you imagine the length of those wavelengths are about the size of bonded atoms. And because they're the size of bonded atoms, we can use infrared light to detect bond energies, or how much energy a bond has. So we're going to say infrared light wavelengths length, I spelled that wrong. Wavelength. Why can I not spell this way? There we go. Wavelengths are approximately, I'll put a squiggly equal sign, approximately the size of bonded atoms Okay, therefore they're used to detect bond energies. Okay, and then we'll go to ultraviolet light. So ultraviolet, these wavelengths are very close together. They're closer together than visible, and our eyes cannot pick those up. And because they're a little closer together, they're more energy and they're a little more damaging to us anyways. But what they're used for and why they're useful is because their wavelengths are about the size of those electron jumps. So remember the size of the orbitals and the size of those rings or orbitals that electrons live in. They're about the size of those electron jumps. Therefore, they can be used to detect electron positions if you use ultraviolet light to do that. So we're going to say wavelengths are about the size of electron jumps. And therefore, they can be used to detect electron positions. Used to detect electron positions. That's what I meant to say. Positions. Bam. Okay. Okay, onto this last page. So, in this last page, we're going to do a little bit of practice. You looking at very specific wavelengths of light that are produced by elements. So, what you did with the glasses, you were just taking a look at the colors, that there were different colors when you excited different elements, but now we're going to be very specific. We've got slightly better tools to look at the specific colors given off by excited elements. These are called spectrometer. No, just they're called. I forgot. I had to look that up. They're called spectroscopes. These guys are used to very precisely look and detect the colors emitted by excited elements. So instead of having glasses where the colors are kind of mixed together, these produce very specific bands, and they actually have a little ruler in there that tells you the very specific wavelengths that are given by each element. You are going to be using one of these, and you're going to be sketching. If you take a look on this back page, you're going to be sketching the spectrum for two elements. The first one's going to be hydrogen. I've got two hydrogen lamps, or I should have set up two hydrogen lamps. So you can. I want you to watch me draw it, and then you can do the second one yourself when you have an example. So how these guys work is you look at it, you're going to have the upside up, okay, and there's a small hole right here, okay, which you're going to look through. And what you'll see is a slit on the right-hand side, and light enters that slit, okay. What you see on the left-hand side is a little ruler that says 7654. That 7654 represents hundreds of nanometers. So 4 represents the 400 nanometer wavelength, and 6 represents the 600 nanometer wavelength, so on and so forth. So when you look through a spectrum, I forgot what the name was again, this thing. When you look through this thing and you line up the light source into that slit where the light enters, it will split up the colors for you, and you can actually measure very specific wavelengths. So we're going to practice here. And I am going to show you the spectrum for hydrogen. I've got a picture of it real quick so that you can see what's going to look like. So if you take a look at the screen here, this is a picture I took of a hydrogen light bulb. So you'll notice here on the left-hand side that there's a slit and there's pink light coming through. Okay, that's where I've lined up the hydrogen bulb, so light is entering from the hydrogen bulb into that slit, and then it splits those colors up, just like when you were wearing the glasses, into the very distinct colors that make it up. So you can see the very distinct red and blue lines, and those represent about, I'm going to say 675 nanometers for red, and blue is just about exactly 500 nanometers. If you trace a line down to the numbers, you can see how many nanometers that wavelength of light is. Okay, and so back to this. And so how you would draw this on a spectrum, and by the way, a spectrum is just the academic term for that splitting up of light. How you're going to draw that spectrum is you are going to either take a pencil or a colored pencil. I'm going to use color because I can. And you are going to draw those colored bands on this spectrum. Okay, so for example, I saw a line at about 5, which means 500 nanometers. So I'm going to draw a blue line right here. Okay, and I'm going to label it 500 nanometers. Okay, 500 nanometers. I also saw a red line at about, I'm going to say, I'll put colors here. I saw a red line about right here between 7 and 6.5, which means it was between 700 and 650 nanometers. So I'm going to say that this red line was at about 675 nanometers. Okay. And just for clarity's sake, I'm going to say that this was, the example was from hydrogen. I'm going to put an 8 for that one. Okay. What you're going to do is you're going to practice yourself. You're going to take a spectroscope and you are going to look at one of the lights around the room and you're going to draw the emission spectrum of that light. There should be somebody around to help you if you can't figure this out, and she'll be happy to help you because I can't, because I am a video. If you can't quite get the light lined up in the slit, you can ask her to help, or if you can't quite read the bands, you can ask her for help as well, and she'll show you how to do it. Just make sure the up is up and the down is down when you look through this. Okay, so go ahead and pause the video now. Take your paper with you and draw the spectrum and label how many, or label the wavelength for me. Okay, go ahead. Okay, welcome back. So hopefully you filled out a spectrum for a different emission, a different gas discharge tube, can't talk, and so you'll have something there. But we're going to scroll down real quick and we're going to practice with the hydrogen spectrum. Okay, and when I say practice, what I mean is we're going to practice using the energy of a photon equation and the equation that relates wavelength to frequency. Okay, so now that we've actually got some wavelengths, we can do some stuff with it. We can do some math problems with this. And so I'm going to do one with you, and then you'll do the last two yourself. Okay, so if you scroll down to practice, it says pick one of the component wavelengths from example 1. So that would either be 650 nanometers or it would be 500 nanometers. Okay, so I'm just going to pick 500 nanometers because it's a round number. Okay, so it says pick one, and please calculate the frequency of a color with that wavelength. So we're trying to find out what is the frequency of a color with a wavelength of 500 nanometers. Okay, so how I'm going to do this is I'm going to need my equation that relates frequency and wavelength, and that is, I'll use black actually. That is C equals frequency times wavelength. Okay, so we always know C is always going to be 2.998 times 10 to the 8th meters. Draw that 8 a little better. Meters per second. Okay. My frequency, or my new Greek letter, is my unknown, so I'll put a little question mark by it. And my wavelength, I do know my wavelength. Okay, so I'll put a little upside down y here, and that's going to equal 500 I'll just erase that, nanometers. Okay, so it really becomes a simple solve for x problem. There's only one slight kink in this problem, and that you have to, whenever you do these problems, you have to turn your wavelength from nanometers into meters. And that's a really simple conversion. I'll do that with you. So if we want to convert nanometers into meters, we have to know how many nanometers are in a meter. And so I'll write that up here. So in every 1 meter, there is a billion, or 10 to the 9th nanometers. Okay, and so if I want to do a conversion of this, I would need to set up my single step boxes. Okay, and I would start with what I'm given, so 500 nanometers. Okay, without even thinking about it, I'm going to put nanometers on the bottom, meters on top. And for every 1 meter, there is 10 to the 9th nanometers, and so I would divide by 10 to the 9th. So I'll use my calculator. 500 divided by, don't forget your parentheses, 10 to the 9th. I get a very small number. I get 5 to the 2, 3, 4, 5, 6, 7. I get 5.00 times 10 to the -7th. Okay, so in meters, that's a very small number, which makes sense because wavelengths are very, very tiny, because photons are very, very tiny. Okay, and so then it becomes a solve for X problem. So I would put C in for C, my V is my unknown, and my wavelength is 5 times 10 to the -7th. So let me do the math here. If you want to do this math yourself, just skip through it. If you need a little help setting it up, you can watch me put it up. So we're going to say that, I'm kind of running out of room. That is okay. We'll do it up here. Up here. Okay. I'm going to say 2.998 times 10 to the 8th equals my unknown frequency times my known wavelength in meters. Sorry, I forgot my unit down here. That's 5.00 times 10 to the -7th. Okay. In order to get my frequency V by itself, I need to divide both sides. I'll use a different color. Oops. Here we go. I'll use red. I need to divide both sides by 5 times 10 to the -7th. And divide this side by 5 times 10 to the -7th. Okay, and when I do that math, I get 2.98 to the 8th divided by what? Oh, let me start over. 2.998 times 10 to the 8th divided by 5 times 10 to the -7th. All right, so I get a final answer of 5.996. Technically, if you want correct sig figs, it would just be 6.00 times 10 to the 14th, and that's per second. So frequency is amount of waves per second, so that would be hertz. Okay. So that would be the answer for that one. Okay. The biggest trick for this one is making sure to remember to turn your wavelengths into from nanometers into meters. That's the biggest trick for these ones. Okay. The last one we're going to do together is number 2. It says, using your answer from question 1, calculate the energy that one photon of this light will have. And so for this problem, what we need is, if we scroll up here, we're going to need this equation right here. Energy equals Planck's constant times frequency. Okay. Whoops. There we go. So we know Planck's constant, it's a constant, it's always given, it's on our equation sheet, and we know frequency because we just solved for it. Okay, it's 6 times 10 to the 14th hertz. So we can solve for energy. So let's isolate our variables real quick. Let me first write down our, let's first write down our equation so we don't forget it. Energy equals Planck's constant times frequency, okay? Where energy of one photon is our unknown. We don't know that yet. H is Planck's constant. Looks like H is Planck's constant. And Planck's constant from our equation sheet is here it is. It is 6.626 times 10 to the negative 34. So a very small thing. Times frequency, which we just said was 6 times 10 to the 14th. So we're going to say 6 times 10 to the 14th. Sorry, it's kind of squished in there. I apologize. It's hard to write on this. So we're just going to plug in chug. So E equals 6.626 times 10 to the negative 34th times 6 times 10 to the 14th. Okay. Which means E equals, if I plug that into my handy dandy calculator, 6.6 fourth divided by, times by 6 times 10 to the 14th. I get, if my math is correct, to the 14th. That looks more like it. So I get that E equals 3.98 times 10 to the negative 19th. Okay, and that's actually joules. Joules is the energy of that photon. Boom. Okay, so that is how you would go from wavelength to frequency, and then frequency to a energy of a photon, a specific photon of one specific color of light. Okay, so if you have time, go ahead and practice 3 and 4. So you'll use a wavelength from the second example that you tried, from the second spectrum that you sketched. And it's the same kind of math, but you'll be using slightly different numbers based on your element spectrum. Okay, so go ahead and try that, and yeah, excellent job today.